So last class we were beginning data encryption standard. Data encryption standard is the old American standard. Currently it's not used anymore as a standard, but there are some applications that still use this. Sorry. This means data encryption standard. It's, as you can guess, a symmetric encryption cipher that works in blocks. Currently, it's considered unsafe, and we will see why. This is based on the facial encryption, so it has two halves. It was developed in IBM in 1974, long time ago, and its original name was Lucifer. The NIST changed the name and changed other parameters, and the new name was this. At that time, just let me tell you, NIST, the National Institute of Standards and Technology, did not exist. The name of the same institute was the National Bureau of Standards, NBS. Now it's NIST. Currently, they have a publication. NIST has many publications of its own standards. The name of every publication is FIPS, F-I-P-S, and they have several publications of FIPS. The standard of this is publication 46, and the last revision is revision 3. So when you see FIPS Pub 46.3, it means this. And because it's a standard, as all NIST standards or publications, this is an open, it's not open source, but it's public. Anyone can see what the standard says. As you remember, last class I told you that DES, D-E-S, encrypts blocks of 64 when the message I'm going to draw here. This is the page that you would like to send and encrypt, and you will take blocks of 64 bits. But these bits get converted into 56 bits. And this is done, I'm going to show you right now. Imagine 1 byte. How many bytes does 64 bits have? 64 divided by 8, you have 8 bytes, right? Yes. So each byte, I'm going to draw 1 byte. This is 1 byte. How many bits does it have? 1 byte. This is 1. Well, I'm going to do it. This is 8. This is 7, 6, 5, 4, 3, 2, and 1. Okay? This byte, we call it the LSB bit, the LSB bit. What does mean LSB? Less significant bit. And this one, how we call it? The MSB. Okay? Remember, in the early years, we are talking 1974, many years ago. At that time, internet was almost non-existent. There was some internet connections, but was not mainstream. And usually bytes were not 8 bits, they were 7 bits. Do you know why? Because the last bit, I'm going to this bit, we call it the parity bit. Okay? And there were many types of parity, even, odd, non, etc. So, does that parity have any information on it or not? Not. Why not? Because it was a control bit. So the parity, this was control. It was used to check for errors, no? Oh. Errors. So in reality, we have 7 bits. So if we have 8 bytes and we take from each one 1 bit, how many bits do we get? 7 by 8. How many? 56. So in reality, we have blocks of 56 bits. Okay, this is the 56 I have here. Okay, you understand that? So we took 64 bits, but in reality, they were only 56 real data bits. The other bits were control bits that we don't want to encrypt. We can encrypt them, but there is no need for. So, Lucifer, origin in the early stage of Lucifer, it was a 128-bit key. But as always, NSA and NIST get into the cipher and modify the algorithm to make it weaker. For a lot weaker. Why they do that? They will not tell us, but you can guess, and any guess you can give could be right. My guess is they want a weaker cipher so they can decipher the this cipher. Okay? So let's start. What you are looking in your right screen is a really global view of what this is. We can identify 2 sides. We can have like a, let me get a, this is the middle side. We have the left side. The left side is, this side is a, we can say the cipher. The cipher side. And this side is the subkey generation. Okay? In the cipher side, we are going to make cipher happen. In the right side, we are going to make the subkeys from the main key. We are going to have one key, 156 key, and from that key, in fact, originally it's a 64 key, but for the same reasons I told you before, 64s became 56 key. So from that original 56 key, we start doing subkeys. How many? In this case, we are going to have 16 rounds. This specifies in its standard to have 16 rounds. So if we are going to have 16 rounds, we need to have a subkey from 1 to 16. Okay, I'm going to show you how to make those. Let's look at the cipher side. The first thing is the input side, the input part. We start here. Okay, let me choose another color so I can highlight it, green color. The first thing is an initial permutation. The 16-bit block that we take from our information, we are going to have an initial permutation on that 64 bits. And you already know what is a permutation. Can somebody guess what do you think will happen there? We will have a transposition. Bit number 1 will become bit 40. Bit number 2 will become bit whatever. So we are going to have a transposition, not a substitution, a transposition. That function, we call it initial permutation. Then we will have 16 rounds. And in each of those 16 rounds, we will do the same thing. For now, this is just like a black box. Later, we are going to have like a, we are going like to zoom inside this round and magnify what is inside. For now, it's just a black box. We are going to have 16 of those. And the input the output of round 1 will be the input of round 2 and so on. After the 16 rounds, we will have a 32-bit swap. So the left side will become the right side, and the 32 left bits will become the right, and the right the left. Okay, it's just a swap. 32 bits go one side, 32 bits go the other way. And then we are going to have an inverse initial permutation. This here we call it IP, the initial permutation. In here we are going to have also IP inverse. The same permutation that we did on the top, we are going to do it on the bottom, but reverse. Okay? And then we have our output, and the output is the ciphertext. So here we have the plain text, 64 bits, and we get 64 bits ciphertext. In the subkey side, we're going to have also 16 different steps. The first is first we are going to take the 64-bit. There's a 64-bit someplace here. We are going to convert that into 56-bit. We are going to do a permutation choice 1. Then we are going to do a left circular shift. So we are going to shift the bits to the left side in a circular manner. So we are not going to drop bits. The bits that fall in the left side will reappear in the right side. You get that idea? It's a circular. I don't know if you saw shift registers. You didn't have never seen shift registers. Well, the thing is, we are going to have a thing like this. Many bits inside. We are going to move this way and we never drop bits. So, okay, something like that. So, how many bits we're going to shift? It depends on the number of the round. We're going to have a schedule, and depending on which round we are, that's the number of bits we are going to shift to the left. Sometimes one, sometimes two, sometimes none. Okay? And we will do that a lot of times. Then, the output of that shifting, it's inputted, is the input of the permuted choice number 2. Okay? And that, the output of permuted choice number 2 is our key, our subkey 1. We are going to repeat this many times, and we are going to have the 16, well, there are many, this is K16, right? Those are the ones we need, okay? So, now we're going to zoom in. And now things get fun. Okay, well, the first one is a initial permutation. The initial and final permutation are the same permutation, but in reverse order. And let's look how we are going to do it. This thing on your right side is the graphical representation of IP, the initial permutation. This is equal to initial permutation. Look, well, I think you cannot look, but let's take one. For example, this bit. Which bit is that one? 18. So if bit 18 of this is the input, and this is the output. Okay? So bit 18 after the permutation, so we follow this line. Someplace there will be bit 6. Let's take another one. 41. Input bit 41. We follow this thing, and will be bit 35, and so on. Each input bit has one permutation that will be the output of that bit. Okay? So everything is like when you play dominoes, everything is scrambled. You have a lot of confusion. Then, you get the idea? You can see the same thing like in an array. This is also IP. In an array, the problem is this thing. I don't like this thing. I want to erase that thing. Okay. Perfect. Remember, let me try to move this one also. We're going to move, no, we're going to move that thing. For example, no. Okay, leave it there. I'm going to do it with G. Remember, this was bit 18, so this is bit 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, let's put the other ones, 20, 21, 22, 23, 20. Okay, so we have bit 1 to 24. We can do the 64 bits that will be 64, right? So what we do is, in this example, let me change colors. Great. This is bit 18. Bit 18, 1 second. So bit 18 now is bit 6. So we can see bit 18, we put it in the 6th position. This is the 6th position, right? Now bit 41, we put it in the 35th position. That will be here. Believe me, this is the 35th position, and so on. Okay, so as you can see, we are permuting not in a random way, because if we do it in a random way, we cannot reverse it. This is deterministic. It's a deterministic permutation. We know what we are doing. Okay, so we can reverse it. So this is the initial permutation. The first 64 bits of the block, we are going to do this. Next, and this is the reverse one. I'm going to move this thing. This is the final permutation of the reverse one. As you can see, we will do the same thing, but in a reverse way. Remember, in the 6th place, we put bit 18. So now bit 18, 8, how will you do it? Well, believe me, it's a reverse thing. Perhaps we can look it better here. This is the reverse thing. Yeah, it's transposed, but where was the bit before? Was the 18 goes to 6? Now 6, this is 4, 5, 6, 7. This. Oh, I don't like that color. Let's use this color. This bit is in the 18th position, right? And what's bit 6? Do you see that's the reverse thing? So every bit is reversed, okay? This is a really easy permutation. Then we are going to have the phone thing. We are going to zoom in this round, and that's quite complicated. Let's do it. All these things you look in your left side is that round thing, round box we saw before, that we call it a black box. So looks hard. It's not that hard. It's just confusing. Believe me. And one thing I forgot. The other day I forgot to tell you about these things. It was like one of the last slides. Remember that we talk about a substitution permutation network. Instead of having a really large substitution and a really large permutation, we are going to have a network of small substitutions and permutations. Okay? Well, the main thing to have here in this network are two things. The first thing is confusion, and the second thing we want to achieve is diffusion. The way we achieve confusion is through substitution. And the way we achieve diffusion is through permutation or transposition. So in a substitution permutation network, what we achieve is confusion and diffusion. This is cipher talking, but in real life you will get also confused and diffused, because after so many transpositions and substitutions you are going to make, you get really confused, believe me. So try it not. Okay, we return to this IP, final permutation. Okay, we have the detail. So let's see. Remember FaceTel? FaceTel, the framework was to have two sides. Divide the block into halves. The right side, the left side, and the right side. So, because we choose to have a 64 block, the left side will be 32 bits, and the right one will be also 32 bits. So, we have, this is the left one, and this is the right one. This is the first one, so we can call it L0 and R0, okay? Then, the left one is really easy. We will just go and put it almost in on that XOR. The right side, we don't do nothing to it. We just swap sides. So this right side, let me change color. This right side will be the left one. Nothing done. Just swap it. And the fun thing happens inside. Here. Let me pen yellow. Here is the fun part. Okay? Remember, this was our dividing line. Here we have that's the division. So what we're going to do now? No, let me choose another color. Green? Green. Okay, so the first right side, how many bits we have here? We have here 32, right? We are going to do a function that's called expansion permutation. This is called the E function. The E function will expand the bits and will also do a permutation on the bits. So from the 32 bits we have in the input, at the output we are going to have 48 bits. And those 48 bits will be permuted. Okay? This output, we add it modulus 2 with an XOR function with the first subkey. The first subkey, this will be K0. What size does the first subkey need to have so we can add it together with the output of the E function? It needs to be the same size. Okay? So this case K will be also 48 bits. Okay? So we add it together and we get this output here. So this one and this one mixed together, and we have this output that obviously is also 48 bits. So the output is also 48 bits. This XOR output will be the input of another function. This function is the SBox function, and this function is a substitution choice box. In this box, in this function, what we will do is first reduce the size from 48 again to 32. And we are going to have, instead of a permutation, a substitution. Okay? So this is the substitution and choice box. These 32 bits, again, will be permuted, just a plain normal permutation. So we get 32 bits. And this output will be the end of the des function, will be the input of this last XOR from the phase-tail structure, from the phase-tail framework. And we have 32 bits here, 32 bits here. The output is 32 bits here. This is just one round. We will have to do this 16 times. So remember, this is a substitution permutation network. Many substitutions, many permutations give the same result as having a really large substitution and permutation. Okay? So, and in the right side, we have the subkey generation. This is not the beginning of the of the key subkey generation, but look, we have two halves. A 28-bit, we call it, instead of calling it the left side of the key, we call it C, because if not, we can get confused with this L. Okay, so this is, in fact, is the left side of the key, and this is the right side of the key. C and D, they both are 28 bits. They were already reduced. At the beginning, there were 64 bits, 64 bits someplace, and were reduced to 56. Okay, remember, we take out the parity bit. So this, we left shift in a circular manner. We input this into the permuted, well, this thing was made in the permuted choice 1. This is the permuted choice 2. In here, we permutate and contract. Why? How many bits we have here? Here we have 28. In here we have 28. How many bits get the input of this one is how many? This is 28, and this is also 28, 15, 6 bits input. And the output we need is a 48. So this will reduce the 56 bits to 48 bits. So the output is 40, well, not there. Here, 48 bits here. Okay? So, and that's it. We repeat this 16 times, and that's this. On the exam, be prepared to encrypt a block. It's not hard. So, this is the permutation expansion. So this is what happens here. As you can see, it's an expansion. We have 32 bits input, and at the output, here we have 32 bits input, and in the output we have 48 bits. As you can see, there are some these things, this one, this one, this one, this one, this one. Some of the bits get duplicated. Okay? You see that? when we look to the table, you will see this bit is this bit, and this bit is this bit. Many of the bits get duplicated, but as you can see, they get duplicated not in any part of the, let me use this one, they get duplicated in these columns. We get two duplicated columns. Okay? Why we want to have them there? Because then we can remove them, because we know where they are. So the substitution is fun. Why? We are going to have the input of the substitution is going to be the XOR function. Remember? Remember here. This XOR function is 48 here, 48 here. We are going to have an output of 48. That's the input of the substitution. So we are going to have here 48 bits. Okay? What are we going to do? We are going to group those 48 bits in several groups, 8 groups. If we are going to have 8 groups, how many bits does each group has? We have 48 bits. Each group is 6 bits. Okay? So imagine this thing here. We are going to have bit number 1, 2, 3, 4, 5, 6. This is our thing here. This is this. Okay? And what we are going to do is to have a substitution using a selection. What will be the selection? We are going to use, let's for example, imagine these bits, example. These bits were, give me any number, binary number. Okay, 10, 1, 1, 0, 1. Okay? That's an input thing. Okay? This is our input. What is going to be our output? Can anyone tell me? The first thing is we're going to divide this, and we are going to check the less significant and the more significant bits. So these 2 bits, they are 1 and 1, okay? And in the middle we have 0, 1, 1, 0. Okay? What value is this? 1, 1? It's 3. And 0, 1, 1, 0?
No, it's 12.
6. Okay? Everybody's following? Okay, so we have 3 and 6. These 3 will be will represent the row, and this one will represent the column. Okay, so another print. Let's change, and this thing we have here are the boxes. We are going to have 8 boxes. This is box S1, box S2, box S3, box S4. For the first 6 bits, we are going to choose box 1. For the second 6 bits, we are going to choose box S2. For the third group, S3, and so on. Okay? So this is the first group. Okay? So in here, we have the example here was this is this will be here 1. This is S1, right? 1 0 1 1 0 1, and the output will be okay. We choose S1. Okay. This is. Let me pick another color. This is 1. No. This is not 1. This is 0, 1, 2, 3. This is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay? So we have row 3. Row 3, this row. Okay? Column 6, this column. So this thing with this is this one. Right? Yes or no? So the answer is 1 decimal. So what we are going to write here,
what if the input is longer?
1 second, 1 second. I'm fighting with this thing. So the answer will be 0, 0, 0, 0, 0, 1. That will be the output. No. That's not the output. Why is not the output that? Why is not? Because this thing has to reduce the size. So the output is not a 6 bit. The output here is a 4 bit. These ones are 6 bits, but the output is 4 bits. So the way we write 1 is 0, 0, 0, 1. Okay? So we get from 6 to 4. Okay? Question?
Yeah, what if the input is longer than
The input will never be longer.
why? Because you have there until
Because we have this, we always will pick 64 bits and we will reduce those 64 bits into 2 halves of 32, and we will expand those 32 bits in 48 bits, so the input will always be 48. Always. If the input is different, you have made a mistake. Okay? So you get the idea how the substitution, the Xbox function works? Okay, so we can continue. Well, that's the other, we have 8 boxes. That's the other part of the box. Okay? There. Well, this is the representation of the P function. The P function is really just a permutation, nothing fancy. We just permute. That's the table for the permutation function. 32 bits go in, 32 bits go out. It's not precise, almost nothing happened, just the permutation. Okay, really easy function. So that will finish the cipher side. Now we have to study the subkey generation. Okay, so for the generation of the subkey, as I already told you, we are going to have the desk key is a 64 key. It's a 64 bits key. This key, the input of this key is taken by the permuted choice number 1 here. This is the permuted choice 1. What will the permuted choice 1 do is convert the 16-bit key into a 66-bit key, taking the parity bits out. Then it will be divided, the right and the left side, C and D. C, this is C, this is D. And here we have the shift. How many bits do we are going to shift? It depends on the round. So we are going to have key scheduler that I'm going to show you right now in the next slide. That will give me how many bits, 1 or 2 bits. The input, the output of that thing will be the input of the next shift, but also the input of permuted choice 2. Permuted choice 2, how many bits we have here? After permuted choice 1, we are going to have 56. So if we divide it in halves, how many?
32.
No. How many? 56 divided by 2 is 28. So we have 28 here, and we have 28 here. We get the input here, and this input will get me here 48, because this thing will contract more the thing. Okay? And you will, and we have to repeat. This is for round 1, round 2, round, this is round 16, this is round 15, and many more here in between. Okay? We repeat the same thing. So how does the PC1, the PC2 looks? I have two of the same, right? Yeah. They look like this. This is permuted choice 1. It's a permutation. It's a reduction. We have here in the top, we have 64 bits. And here we will have 56 bits. All of them permuted. Okay? And that's it. That's the permuted choice 1. If we look the table, well, this is permuted choice 2. Let's look at the table. The tables, I'm going to put here permuted choice 2. This is put here. No, I want to change these things. This is permuted choice 2, and this is the schedule. Permuted choice 1, what will it do? Look, who can tell me? Who can tell me? What do you think it does? How many bits? Here we have 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 8. And here we have 32 bits. And here we have 32 bits. Okay? And they are permuted, right? The permuted choice 2 will be this. Okay?
Up to 28.
That's
No, in each.
Yeah, we need to have 28.
Several times.
Okay, as I can see, there's a mistake here. Let's remove this. Let's erase this thing here. Which is the eraser? This one. Eraser. Eraser. This one. Let's erase this 32 because, in fact, we do not have 32 bits here. If you count them, there are 28 here and 28 here because we removed all the multiples of 8 and all the multiples of 8, they are removed. Okay? Those are the parity bits. Okay? So we have the permuted choice 1. Permuted choice 2 is there. The schedule is here. So, for example, for the first round, how many bits are going to be shifted to the left? Just 1. For example, round 11, how many bits are going to be shifted to the left? In this case, 2. Okay? There are only 3 cases where they are shifted just 1. Round 1, round 2, and round 9. Okay? In other cases, they are always shifted 2 bits. Any questions? So, we know how to make subkeys. We know how the des function works and how it's inserted into the Pastel framework. So, knowing that, we can cipher anything with this. As you can see, it's no mathematics involved at all. No, nothing weird. Just, I guess, if you show how to do this to a kindergarten boy, he will be able to do it. It's just substitutions, really. At least in, well, substitutions, permutations, that's it. And I guess any one of you knows how to do that. I hope so. It gets complicated because there are many substitutions and many permutations. And just one bit wrong at the beginning and everything is wrong. So any mistake, you carry on the mistake forever and ever. Okay? So just one bit can be very bad for you. Okay? So